Last few weeks, we have been discussing about regression, and this week we will kick in the other area, what we call classification. If we want to get a quick difference between regression and classification, most of the things are actually common. Only the difference is with the response variable or target variable y, and we'll learn quickly. So if we recall, for regression, we were predicting real or floating point values. And for classification, we will be predicting or modeling some categorical value. Those are actually predefined. On regression, two of the problems that we discussed, one is that the diabetes score prediction, and the other one is the healthcare cost predictions. So as you see, these are actually both numerical or floating value predictions. So this goes under the regression category. And for classification, I think the examples will be much more intuitive. So one example is the digit recognition. So you have 0 to 9 digits. So this is a practical example of a classification task. And there you will find a lot of yes, no, or binary problems. For example, whether the loan is accepted or rejected. So this is a loan prediction problem. Then you have a positive or negative sentiment. So both of these two are actually binary classification problems. Another intuitive example we'll be looking at, you want your classifier to classify between two animals, dogs versus cat, and still this is a binary classification problem. So these are some examples of classification problems or classification tasks. As I said, that we are slowly moving from regression to the predictive modeling of classification tasks. But although we covered most of the regression items, it's not fully done yet, because some of the elements we'll be learning from our classification lectures that are equally applicable in the regression task. And some of the things that we have already learned, for example, the data normalization, the data or categorical feature encodings, these are all equally applicable to both regression and classification tasks. So here the problem is that we want to classify between dogs and cats, and the data are actually plotted on a two-dimensional Cartesian plane. Let's not focus on the features, but we're just showing their images. We can clearly see that the pictures can be separated by a straight line, and if this straight line is your model, just like your linear regression model that we learned for regression tasks, we can say that the cats are actually on the left side of this model, and then the dogs are actually on the right bottom side of this model. For this particular scenario, we can have a linear model that can separate these two classes. So we are good. Okay. But how is that? So now we have added two more examples, and you can see that now you will have a hard time to separate these two classes by using a line. Okay. So there are few options. For example, here our data is on the two-dimensional plane, but we can extend, and some of the models like support vector machines can produce a linear classifier, but to get a simple understanding, we can still have a model in the two-dimensional plane, but our model not necessarily need to be a linear model. We can have a non-linear curve or model, just like here. Even in the 2D, we can separate the cats from the dogs. Okay. So that's the idea, And we just saw one particular example where we have a clear linear classifier can be learned, and the other one is where we will need to either have a nonlinear classifier, or we might need to do additional steps to actually get a linear model. Moving forward, we will be learning about a few different classification models, namely a logistic regression, random forest classifier, support vector machines classifier, boosting, and naive Bayes. As time progresses, we'll be actually unwrapping the underlying mechanics of each classifier, but we will also need to know, because of the time constraint, we might not be going to the entire depth of each model. In summary, I think we use random forest regressor and support vector machines and boosting. These three models we have used in our regression tests, but the underlying mechanism is quite the same or similar, but we will need to actually do a little bit more understanding of the other two classifiers. So first classifier, what we call logistic regression, and here we are talking about regression, but why and how it is becoming a classifier. And again, we'll be giving you more information and more reading materials or maybe resources so you can better understand. But let's understand this concept to an extent today. If you recall, in our linear regression model, we had two parameters, beta 0 and beta 1, and we can clearly see that you have a similar term as you had in our linear regression model for one parameter. But here what's happening is we are actually using the linear regression kind of parameterization, but not directly as we used in our linear regression model, rather at the exponent parameter. And we can think it as a functional of the linear regression, and it is actually transforming into another function values with ranges between 0 and 1. So this is the famous sigmoid function. So you will learn about this function when you will be learning the neural network or other complex models, but the starting is actually through the logistic regression formulation. So here what we are saying, that we are learning the regression but using the regression functionality to learn another level of a function that is actually transforming the values to a probability value within the range of 0 and 1. And if we have these values, transform values plotted between 0 and 1, we can use a threshold 0.5 to actually separate between two classes. So you have a regression and then you transform using the sigmoid function, and the value is less than 0.5, then this is into one class, and if it is more than 0.5, then it goes to the other class.